All right. Good afternoon. Um, any question before we start? I returned the homework one, so if you have any question about grading, you can ask me after the class. All right. Let me finish the signal processing. So we learned how when we are given with periodic function, the motion which is going to repeat itself regularly, how can we convert the periodic function or motion to harmonic motion by applying the Fourier series. So that can be applied for continuous function, but what if we have discrete points? So what if we get the data by measuring, so something like this. So at time t1, you know that x, the location of the system is going to be at x1. At t2, it's going to be at x2, t3, x3, t4, x4, and so on and so on. So suppose the more, and after you just connect the points or fit the graph to the points, you will get something like this. And then you will see that this motion is going to repeat itself after that. The same thing, the same pattern, it's going to be repeated after that. So we are going to have periodic function, but we have discrete points rather than the continuous function. So how can we get the Fourier series coefficient, or how can we get the coefficient for harmonic analysis? So for those things, A naught is going to be 2 over n. N would be number of points or number of data or number of discrete points that you will collect. So 2 over n. The integration is going to change to the sigma because we don't have continuity in the problem. Y I goes from 1 to n. Xi, I mean, if I want to. So whatever is the value of the function at each specific point, you can plug in there and find A naught. So then an, it's going to be 2 over n. The integration is going to change to summation 1 over n yi cosine of 2 n pi ti divided by capital T. So what? Let me change it to x. Xi is the value of the function at the corresponding point. N is the number of data that we have. T is the time at the specific time. And this capital T is the period of oscillation. Is T. So this is the T. Depending on what would be the period of oscillation, you can measure that T. So you have this T. So for each n, you can find the corresponding A. So Bn is going to be something like this, except cosine is going to change to the sine. Good? So if you have a discrete function, if you collect the data by measuring, then this is how you can do the harmonic analysis and find the coefficient for Fourier series. All right. Let me talk a little bit about frequency a spectrum. Suppose we have done the harmonic analysis for a periodic periodic function, and we got a naught plus a1 cosine of omega t plus b1 sine of omega t plus a2 cosine of 2 omega t plus b2 sine of 2 omega t an cosine of n omega t plus bn sine of n omega t. So we know what would be the value of a naught an, a1 to an, and b1 to bn. So you remember when we are given with two harmonic motion, harmonic function, this is cosine, this is sine, and if they have the same frequency, both they have omega, we call them synchronous. So we can add them and come out with one single harmonic function with something like this: d1 cosine of omega t minus phi1. So because these two have the same frequency, I can add them up such that to get d1 and phi1 as a function of a1 and b1. How can we do that? If I expand this, it's going to be, I've done this before, I'm just d1 cosine of omega t cosine of phi plus d1 sine of omega t sine of phi. Good. So d1 cosine of phi should be equals to a1. d1 cosine of phi should be equals to a1, and d1 sine of phi 1 should be equals to b1. So if I want to find d1, I can square them. a1 squared plus b1 squared is going to be d1. If I square them and add them up, I can get rid of this. And if I divide this by this, b1 over a1 will be the tangent of phi1. So phi1 will be the tangent inverse of b1 over a1. So this is how I can find d1, this is how I can find phi1. So I can replace this with d1 cosine of omega t minus phi1. Same things here. d2 cosine of omega 2 omega t minus p2. a1 and b1 change into a2 and b2, and you can find d2 and p2. And the last term is going to be dn cosine of n omega t minus pn. The same approach you can find the magnitude for dn. So as you see, each term is going to represent the corresponding frequency. So this term, it's a harmonic function, it's a cosine, with the frequency of 1 omega. This term is representing a harmonic function with the frequency of 2 omega, and this term is representing a harmonic function with the frequency of n omega. So they have some values. We would like to know which coefficient is dominant, which amplitude. We call them amplitude, this coefficient. for that reason, we introduce frequency spectrum. On this graph, instead of having time, we are gonna have omega, which is the frequency of first term. So this is gonna be omega, 2 omega, 3 omega, up to n omega. And in y-axis, I'm representing the amplitude of each harmonic function. So whatever is the value of d1, I just locate that. For example, this is d1. This is d2. So I'm just representing the value of d1 to dn on this graph. So if you look at this graph, you will see that the term with the frequency of 4 omega has the greatest amplitude. So this frequency in this periodic function is dominant compared to the other frequency. You can plot this for phase angle. If you remember, we call this as a phase angle, phi. So you can see how the phase angle is changing with the omega. Good. So these are the terms that you might see on the signal processing. In signal processing, we might have time domain versus frequency domain. Suppose we have a function like this. It's a harmonic function. It's a sine function. So a sine of omega t plus phi1. If I ask you to draw the this motion as a term of time, this is going to be time. This is going to be x of t. So we know that x would be a sine of omega t plus phi. Phi1. Phi naught, whatever. So it's going to look like this. So it's a sine function with the amplitude of a and phase angle of phi naught. So if I ask you to draw this harmonic function in frequency domain, so the time axis is going to change to the frequency, and this is going to be the x, instead of a function of t, it's going to be a function of frequency. So what would be, if this is, for example, if this is omega, for any frequency different than omega, we don't have any amplitude. So this is going to be 0, because the only term that we have here is for frequency of omega. So for omega, it's going to be a, but for other frequency, we don't have any amplitude. So this guy is going to represent the frequency domain of this harmonic function. So for harmonic function is not useful because we already know that which frequency is dominant because there is only one term. But for this one, for example, this guy, it's a periodic function because it's repeating itself. We apply the harmonic analysis, we find A0, A1, B1, A2 through AN and B2 through PN, and then we can find D1, D2 through DN. Or we can have A1, A2 up to AN, and B1, B2 through BN. So if I draw the frequency domain for A, I will get something like this, for example. And for B, it's going to look like this. So by looking at them, you can see that for frequency of omega, the coefficient of A1 and B1 are dominant. Or if you want, you can add them up, you combine these two harmonic function and come out with one single harmonic function and just look at one single amplitude corresponding to the frequency. So this is a time domain versus frequency domain. Any question about this? All right. Now let's start free vibration for 1 degree of freedom system. So we are done with the introduction part. We covered the signal processing, and now we are ready to start free So if you remember, the vibrational system has 3 components: a spring, damper, and the mat. A spring with a stiffness of K, and damper with the damping constant of C. We will look at the C later, but for now we just consider this system. This is 1 degree of freedom system because if you know the X, the location of mass M, you can figure out the location of the other terms, which is the spring and the damper. So it's a 1 degree of freedom. It's defining 1 degree of freedom. Free vibration, since there is no external force applied to this, we call this free vibration. There is no external force. If I apply external force to this, then we don't have free vibration. But when we have no external force applied to the system, we have free vibration. I will start with the system with only mass and spring, K and M. We call it undamped free vibrational undamped system. C is free vibration, means F of T equals to 0. Undamped system means the constant of C equals to 0. And 1 degree of freedom, we don't have any more. We don't need any more coordinates to define the system. And now, let me start with suppose there is a spring with the constant of stiffness of K. The spring is at relaxed position. It's at equilibrium. So this is the free length of the spring. Then I will add 1 mass. Due to the weight, the spring is going to have some deflection. So we label this as a static deflection. Delta is static deflection. Why we do have static deflection? Because of the weight of the mass. How much would be the static deflection? We know that force, if I draw the free body diagram of this, mg is going down, force coming from spring should apply from the opposite direction. Summation of the force must be equal to 0. So I consider this direction as a positive. So this direction as positive. So I'm going to have positive mg minus F equals to 0. F would be mg, and F is corresponding with the deflection times K. K times the deflection of the spring. So K times the static deflection would be mg. So delta static would be mg divided by K. This is the static deflection of spring. Then you add the mass. Now, when this system is at equilibrium, add some more displacement to spring. So add more displacement. From here. X naught. Just add extra displacement on the system and keep it there, and then release that. It's gonna start oscillation. So if this is the spring, I'm gonna add the mass to that due to the weight. We are going to have some static deflection. In this case, it's 10 centimeter. So then I'm going to remove this by 20 centimeter more, and then what I changed, the friction, it was at high friction, so you could see that it stopped the motion, but I changed it to undamped system, then C equals to 0. So now if I extend by 20 and release that, it's gonna start oscillation. So we would like to know when the mass m is at a specific location like x, what would be the speed, what would be the acceleration applied to the mass at a specific time. So time. So this is what we are going to do by doing the free vibration analysis. So at time 1, at time 0.5, we would like to know the location of the mass, the velocity, and acceleration applied to the mass. Good? All right. There are two methods that we can apply. One is a Newton method. Both methods are important. Some problems should be applied by Newton method. To derive equation of motion. So we would like to derive the equation of motion. So how can I derive the equation of motion? I should have the free body diagram of this. So free body diagram of mass M. One weight, one force due to the weight is going to apply to the mass mg. So let me, I'm gonna measure x from this position. Before that, I measured the x from this line, but after we apply the mass and due to the weight we have a static deflection, I'm gonna start measuring the x from this line. So x is gonna be the new deflection on the mass. So how much would be the force coming from the spring? One force is gonna be k static deflection k x. One force due to this deflection, one force due to this deflection. And as I said, it's gonna, this direction is gonna be positive. Summation of the force due to the Newton's second Newton's law is gonna be mass times acceleration of the mass. And acceleration is second derivative of x. First derivative is velocity, second derivative is acceleration. So mg is positive, summation of the force, mg, minus k static deflection minus k x equals to m x double dot. You remember here, the static deflection would be mg divided by k, or mg would be k static deflection. So these two are the same, except the sign is different. So if you add them up, you will get 0. So if I simplify this, it's going to get mx double dot minus kx equals to mx double dot, or mx double dot plus kx equals to 0. And this is the equation of motion for this system. Good? So if you look at the equation of motion, no term of static deflection is showing up there. So the system, the equation of motion is not dependent to the static deflection. So, and the weight of the mass. See, there is no mg is gonna showing up here. So for future, when I want to derive the equation of motion, I can just neglect the static deflection and the weight. Just look at the motion of the system without considering the static deflection and the weight, and I'm gonna get the same things because they can be cancelled out on the equation of motion. I started. You are gonna derive the equation of motion for different mechanical systems, but using the same approach. So if you have any question about this, it's time to ask. Alright. The second method that you can use is the energy method. I'm gonna differentiate the equation of motion by applying the energy method. So again, I assuming that the motion is gonna start at this point when we apply the static deflection and we got this, then the motion is gonna start from this point. So I don't consider the static deflection and the wave. So when this guy is at the distance of x from this line, how much would be the potential energy absorbed in this system when the mass is at the location of x? What would be the potential energy of mass spring system when the mass is at the position of x? That some parts of that is because of the gravity, as you said. But what I'm saying that we don't consider the gravity and static deflection for the analysis. I can show you that if we consider that, we still get the same result. So besides the gravity, what would be the potential energy which has been absorbed on the system? 1/2 kx squared, because you made deflection from this point, which is the reference point. You made the deflection of x, so you absorb some potential energy on the system. Half of how much would be the potential energy absorbed in the spring? Half times the stiffness times the magnitude of deflection, which is x in this case. Kinetic energy is mass is the term which represents the kinetic energy. It's going to be half of the mass times the velocity of the mass. The velocity of the mass is x dot, so I should square that. Half of mv squared. The velocity of mass is x dot. So when we don't have any damping or any friction, suppose there is no friction due to the air, the summation of potential energy and kinetic energy is constant. We have conservation of conservative energy on the system. So the summation of potential energy and kinetic energy is constant with assumption of no friction. So the potential energy and kinetic energy at entire of the motion, the summation would be this constant. They just convert to each other. Good? Now, since it's not changing with time, it's constant, if I differentiate this part with respect to time, it's not changing over the time, this part is going to be 0. So derivative of potential energy plus kinetic energy with respect to time is going to be 0. If your system is there is no friction or there is no we don't dissipate the energy on the motion of the system. So potential energy plus this half of mx dot square. If I differentiate this with respect to time, I set it equals to 0. This is constant, this is constant. Derivative of x squared would be 2 times half of kx, derivative of x with respect to time, plus 2 times half mx dot, derivative of x dot with respect to time, and this is going to be equals to 0. So 2 times half is 1, 2 times half is 1. Dx over dt is x dot. How x is varying with time, it's a velocity, x dot. I have one x dot here, one x dot there. I can cancel them out from both sides. So I can cancel out these two. On the right side, on the left side, I have kx plus m, derivative of velocity with respect to time is the definition for acceleration. How fast velocity is changing with time. It's an x double dot. So I will get kx plus mx double dot equals to 0. And this is the equation of motion that we derived right there. Good. So this is the equation of motion for the system. It's a second order differential equation. For some system, you need to apply Newton method to differentiate equation of motion. For some other system, you have to use the energy method. The energy method is going to apply for the system where we don't have any loss of energy. If there is no friction, you can apply energy method. Otherwise, you cannot, and you have to use only Newton method. We will go over some examples after we, maybe sometimes next week. But now, for this differential equation, as you see, it's a mx double dot plus kx. It's a second order differential equation. It's a homogeneous because right side is 0. We would like to find the response of the system. How x is changing with time. We would like to find this. For any given time, we would like to find the value of the x. So we are looking for solution of equation of motion, and equation of motion for this system is mx double dot plus kx equals to 0. This is a second order homogeneous equation. We assume that the response of the system is equals to c e power lambda t. For homogeneous system, second order differential equation, we assume that the response or the solution of the system is going to look like this. We plug in here and we find lambda for that. So I'm going to find the value of the lambda and c to satisfy this equation. So x dot is going to be c lambda e lambda t. X double dot will be c lambda square e lambda t. I differentiate this once. I differentiate one more time to get mx double dot. So now plug in there. Mx double dot mc lambda square e lambda t plus kx kc e lambda t equals to 0. C is constant. E lambda t can be cancelled out from both sides. So I will get m lambda square plus k equals to 0. So lambda square would be negative k over m, one positive number, which is lambda squared, got negative value. So we should use the imaginary number. So complex number. So lambda would be s square root of negative k over m, or s square root of negative 1 times s square root of k over m, positive and negative. So s square root of negative 1 is I, so it's going to be positive and negative I s square root of k over m. So there are two roots for this one. Good? Everybody can see why this I is going to show up because of negative 1. So for this system, mass and spring, we define this as an omega n, or angular frequency. It's just definition. Omega n is defined as the s square root of k over m, or we call it angular frequency. So I can replace this by positive and negative I omega n. Later on, I'm gonna define natural frequency of the system. Sometimes natural frequency is different than angular frequency, but sometimes the people using the same terms for omega n as well. So natural frequency is different than omega n because you know that Fn is 1 over T. Natural frequency is 1 over period of oscillation, and period of oscillation is 2 pi divided by omega n. So Fn is a natural frequency, but sometimes people are using this term for the natural frequency. So back to this, let me plug in positive and negative I omega n on the response of the system. So x of t would be C1 e power positive I omega n plus C2 e negative of I omega n. Summation of these two can be general solution for that homogeneous question. So C1 is the coefficient, C2 is coefficient for this, C1 is for positive. So if you remember, e power I omega nt can be written as cosine of omega nt plus I sine of omega nt. The other form of complex number. And negative I omega nt is going to be cosine of negative omega nt plus I sine of negative omega nt. Negative omega nt, negative omega nt. Cosine of negative, we know that cosine of theta equals to cosine of negative theta. Cosine of 30 is equal to cosine of negative 30. So this is going to be positive omega n. But sine of negative theta is negative sine of theta. Sine of 30 degree is equals to negative sine of negative 30. So I can move this here. So then replace this here. C1 cosine of omega nt plus C2 sine of omega nt plus C2 cosine of omega nt minus C2 sine of omega nt. This is this guy, and this is this line. So these two have cosine of omega nt. It's going to be C1 plus C2 cosine of omega nt plus C1 minus C2 sine of omega nt. I missed I. And then C1 plus C2 I assume as a new constant. It's a constant. A, and this part as another new. I times C1 minus C2 as a sine. So it's gonna look like this. A cosine of omega nt plus B sine of omega nt. So the response of the system is gonna look like this. A and B are constant. So we have started from mass and spring system by applying two methods, Newton method and using energy method. We could derive the equation of motion. This is the equation of motion for mass spring system. Then we have free vibration and no damage. Then we were going to find the solution or response of this equation of motion. By applying this, I could find the response or solution of the equation of motion. If you plug in any time t1, you plug in t1 here, you find the sine of that, cosine of that, you multiply this by b, you multiply this by a, you find the location of mass, and you are done. If you want to find the velocity, differentiate this once. If you want to find the acceleration, you differentiate it twice to find the acceleration of the mass at time t1 time. So what would be the A and B? A and B can be calculated by considering initial conditions. So mass spring system. The static deflection is 10. So how the motion is just started, I just removed this by 20 centimeter, and after I release that, it's gonna start oscillation. So the motion is gonna start at this time. So time 0 is gonna be at this point. At time 0, what would be the value of x? It's gonna be 20, true? So this is the initial condition. What would be the velocity? 0, it's not moving. So these two are two initial conditions. By two equations, I can find A and B. So when I remove that, it's gonna start oscillation, and this is the equation of motion, and this is the response of the system. So how can I find A and B? at time 0, in this example, x of 0 should be x naught. In this case, 20 centimeters. X naught is the information that you are given at time 0. At time 0, the velocity must be 0. You might be given by different initial condition. I might say, in the motion that we have at time 1, x has this specific position, velocity has this magnitude. But typically, these are the initial conditions. Now, let me plug in time equals to 0 in this equation. X at time 0, x naught, x at time 0 would be a cosine of omega n times 0 plus b sine of omega n times 0. Sine of 0, omega n times 0 is 0. Sine of 0 is always 0. So b times 0 is going to be 0. So this is going to be 0. Omega n times 0 is 0. Cosine of 0 is 1. A times 1 is going to be A. So right side is A. Left side is x at time 0, which is x naught. So x naught would be A. So I can find A simply by this value. A would be x naught. In this example, it's going to be 20 centimeters. Now, I need to find the velocity equation because I need to plug in the second initial condition. So velocity is x dot. This is constant, it's 20 centimeters. Derivative of cosine omega n t with respect to time, it's going to be negative omega n sine of omega n t plus b is constant. Derivative of this is going to be b omega n cosine of omega n t. So this is the velocity equation. At time 0, x dot of 0 is v naught, 0. Let me work with the general case. V naught. In this example, v naught is going to be 0, but the velocity at time 0, it's given to us. Plugging t equals to 0. X naught, not x dot at time 0 would be negative x naught omega n sine of omega n times 0 plus b omega n cosine of omega n times 0. Sine of 0 is 0. So whatever times 0, it's going to be 0. So this term is gone. Cosine of 0 is 1. B times omega n would be times 1. It's going to be omega n. So V naught would be B times omega n. So B would be V naught divided by omega n. So if I want to rewrite this equation, the response of the system is gonna be this. X at any specific time would be A x naught cosine of omega nt plus B, which is V naught divided by omega n t, omega n naught, omega n t, sine of omega n t. And this is the response of the system. Good. Any questions so far? All right, now let me define something. I define angular frequency, square root of k over m. As you see, the angular frequency is just depending on the specification of the system, which are the stiffness and the mass. Period of oscillation, it's 2 pi over omega n. Natural frequency of the system. This is the term that you will hear in vibration. So natural frequency would be 1 over t. So if I flip this, omega n over 2 pi, omega n is square root of k over m divided by 2 pi, natural frequency of the system. So this is the right definition for the natural frequency, square root of k over m divided by 2 pi. But sometimes people using omega n as a term for the natural frequency. But as you see, it's different. We need to divide it by 2 pi. Good? The response of the system is summation of two harmonic motion. This is harmonic because the cosine. This is harmonic because it's the sine. Both harmonic motion have same frequency, omega n. So I can add them up to get to come out with one single harmonic function. So if the function that I want to get is something like this, a cosine of omega n t minus phi, I need to find a and phi corresponding to this response. So if I extend this, I will get a cosine of omega n t cosine of negative phi minus a sine of omega n t sine of negative phi. If I expand this. So a cosine of omega n, cosine of negative phi is gonna be same as cosine of phi. So I will get A cosine of omega nt cosine of phi. Sine of negative phi, it's going to be negative sine of phi. By this, it's going to be positive sine. So A sine of omega nt sine of phi. So this must be equals to response of the system, which is x naught cosine of omega nt plus v naught divided by omega n sine of omega nt. Left side equals to the right side. Here I have cosine of omega nt. On the right side I have x naught cosine of omega nt. So A times cosine of phi would be x naught. Same things. A sine of phi would be v naught divided by omega n. How can I find A and phi? A would be A squared would be S square root of x naught squared plus v naught omega n squared. If I square both sides, add them up, I can get rid of cosine of phi and sine of phi. I will get A squared, right side with this squared plus this squared. And then I apply a square. This is A sine. If I divide this by this, A can be cancelled out. The tangent of phi would be v naught divided by omega n divided by x naught. Which is v naught omega n x naught omega n. So phi would be tangent inverse of v naught x naught omega n. So this motion, the response of the system can be written as one harmonic function. X of t would be A, which is this guy, times cosine of phi, omega n t minus phi, and phi is the tangent inverse of this guy. So these two are the same, except this one is representing one single harmonic function. Sorry.
So your phi naught equation, you have a different than what the book has it written. The book has it written of the inverse tangent of x naught omega n over v naught.
Okay, if you look at the book has sine instead of cosine.
Okay. So
I mean, that's a, I can show you, we can get the same things. Suppose I would like to write this, the summation of these two, as a function of sine, not cosine. Okay? So let me do that. So suppose I would like to write it as this guy. B sine of omega nt plus phi. Okay?
yes, okay.
If I expand this, I will get B sine of omega t cosine of phi plus B cosine of omega nt sine of phi. Okay? This is B cosine, this is B sine of omega t. So B sine of omega nt should be equals to V naught divided by omega n. And this guy, B sine of, B cosine of omega nt cosine. And this B sine of phi, B sine of phi should be coefficient of cosine of omega nt, which is x naught. If I want to find B, I should square both sides to get B. I'm gonna end up to the same things. But for the phi, B over B sine of phi divided by B cosine of phi would be x naught divided by V naught over omega n. I cancel out B, I will get the tangent of phi. So phi would be tangent inverse of x naught omega n divided by V naught, which is inverse of that. So if you like to write the response as a cosine term, you should come up with A and phi that I showed you on the left side. If you want to write it on the sine term, you can use this one. All right. Any other question? So let's look at this. All right. Suppose this system is at the rest. So I'm gonna move it by I'm gonna move it by 10 centimeter and release that. It's gonna start oscillation back and forth. So when I'm gonna count the number of cycles, every time that this mass is gonna touch this, one cycle can be counted. True? Every time that this mass is gonna reach to this, I'm gonna count one cycle. So I'm gonna count 10 times to measure the period of oscillation. What was the t? How much is the time needed to complete one cycle? I'm gonna count 10 times and then I divide it by 10 just to decrease the error of counting. So 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So period of oscillation for 10 is 6.34. For t is going to be 6.34 divided by 10, which is 0.634. So this motion is going to take 0.634 seconds to complete one cycle. True. So let's back to the original system. Now this time instead of 10 centimeter, I'm gonna have 20 centimeter extra. 30 centimeter. So if I release that, what would you expect for period of oscillation? Are we gonna have more than 0.634 or less than 0.634? Less or more? Let's see. So next, again, I'm gonna count 10 times. When it reaches to the top point, I'm gonna click hit and count 10 times. 6.34. Let me reset that. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 6.26. It's very close to what we got for this. 6 to 6. Look at the t. What was the t? T was 2 pi over omega n. 2 pi for both systems are the same. What is going to be the omega n? Omega n is a square root of k over m. For both cases, k and m are the same. So no matter what would be the your x naught or initial condition, as long as m and k value are not changing, you will get the same frequency for the system. Good? Any question so far? All right, we continue on Wednesday class.